slide from last class. So we were talking about this new model for our bonds, the nuclear motion of the bonds, right? This is the motion of the two nuclei, the two atoms stretching mechanically away from each other in a diatomic. Right, we started with that harmonic oscillator approximation, and we realized that it never breaks. No matter how hard you stretch it, it just gets more and more excited. Of course, that's not how bonds work. Bonds, eventually, you pull them hard enough, they break. So by considering the limiting effects of the potential energy, that the potential energy goes to zero at infinite distance, that it skyrockets extremely fast at close distances, and at distances near equilibrium where the bond likes to sit normally, it looks harmonic, right? So we have this kind of changing potential as a function of stretch. And a really nice logical way for us to come up with this formula model is this Morse oscillator, which is what we traditionally use to model these bonds, which gives us this nice behavior that gives us everything. Describes the bond in a way that we would physically. And the end result of kind of the big conclusion for how can we know that a bond looks like this experimentally is the fact that when we use the Morse oscillator, we predict that the spacings between the energy levels as you increase in energy start to get closer and closer together. The gaps start to close. And that's contrary to the harmonic oscillator. The harmonic oscillator, they're equally spaced by the frequency, right? They're like octaves of the same note. But here what you have are intervals that are closing as a function, smoothly as a function of the energy or the quantum number V, eventually to the point where that when you reach the bond dissociation energy, you transition into a region where you have two free atoms and you have a continuous band of kinetic energies there. Right? So the system goes from perfectly discrete in some sense to perfectly continuous as a function of energy. As it smoothly moves from bound in a bond, covalent bond, to unbound with no bond. Right? And the idea is that right, we call this anharmonicity, right? The deviation from harmonic, from the quadratic potential. And the way that we measure that spectroscopically is by measuring how the energy levels collapse as a function of energy, right? That the spacings get smaller and smaller, right? And the shape of this potential, right? How high the potential is, the strength of the bond, how anharmonic it is, are things that we can measure spectroscopically. Right? We can derive them from the things that we see in our spectrum. That's going to be something we'll focus on when we get back from spring break. All right. So our last lecture or so on the harmonic oscillator, let's say the last two lectures, I think we'll spend next week on it. Not next week, 2 weeks. Will be about how do we pull this information out of the spectrum? How does the spectrum teach us these things? All right, we'll see some hints of that today. I just want to get us all on the same page before we do that. So I have just a very small example to show you, and then I have a small little lecture I want to give about energy, units of energy in particular. It's a little bit dry, but what we're going to find in this class, you've probably already seen this, is that we use a very heterogeneous set of units. We don't just use joules per mole like we do in thermal or general. Kilojoules per mole, in some sense, are not a useful unit for quantum mechanics. But that doesn't mean it's not meaningful for us to consider things in kilojoules. It's just that there are more convenient units to use for energy. And I want to talk a little bit about those different types of energy units and how we convert between them. Again, very dry, but it's very, very useful because as we progress through this class, we're going to see different types of energy units. I'm going to use them interchangeably, and I want everyone to be on the same page. Because what we're going to find is that the SI scale, the SI units, again, are very nice. You do lots with them, but they're not always convenient. Right? When we're communicating with each other about information, when we're being scientists and sharing stuff, it's really not helpful to talk about things that have exponents like 10 to the minus 35. Right? It's just not a useful number. Right? Someone's going to screw it up. You can already know that in your homework. Everyone screws up factors of 10. Even I do it. And so we're going to try to choose convenient units, convenient standards that allow us to represent numbers in kind of a very kind of simple way. units that are meaningful. So let's talk about these units today. That's the wrong button. And my motivating source of this discussion is light. The idea of having a wave that contains energy inside of it, right? An energy containing wave. So all of this conversation is going to be derived from our discussion of electromagnetism. I'm just going to kind of call this the energy of light. And its units. It's probably not lost on you that when we talk about systems quantum mechanically, and we want to do it practically, we want to understand a molecule in its microscopic nature, we're going to appeal to spectroscopy. That's what we always do. Spectroscopy, we're using light as an analog for energy. So it's very reasonable to think about the energy of light because it's what we're using to probe these energy levels. Right? We can tune our light, the wavelength of the frequency of our light. And we're going to see if energy levels are resonant with that light in spectroscopy. And so it's very logical to do everything in terms of the units of the light that you're using. And everything around light is built around one equation for its energy, which is Planck's law. Right? The energy is equal to h Planck's constant times the frequency. Bless you. Right? Remember, this is the frequency in hertz, which is the equivalent of 2 pi radians, how fast you go through 2 pi radians for 1 second. Right? So it's a whole cycle of a wave per second. Energy, of course, here is in joules. Right? The units of this are joule seconds. And of course, hertz, another way to write hertz is just inverse seconds. Right? So E is in joules, right? Joule seconds times inverse seconds is joules. Right? There's another way to write this, depending on our context. We can also write this h bar times this omega. And this is the frequency in radians per second, which we also call seconds. But notice that this is that omega is v over 2 pi. Right, so they're related by a factor of 2 pi. Right, and that's where that h bar comes from. Right, h bar is h over 2 pi. Right, that's where this 2 pi is. Right, it converts between cycle frequency, which is what we typically measure in an experiment, and this omega, which is a more convenient unit when you're working with angles, sines, and cosines. So again, let's look at how these two types of units interconvert, right? How much energy is contained, or let's say this, what's the frequency of something that's 1 joule, or vice versa, right? Let's just do those conversions really quickly, and then you'll start to understand why this is joules are not a useful unit for us. Right, so if we have 1 joule, this is equal to h times our frequency. Right, so our frequency is 1 over 6.626 times 10 to the minus 34 joule seconds. Right, that's a really big number. Let me just pull my calculator. All right, that's a huge number. That's a frequency of 1.51 times 10 to the 33 hertz. Right. I'm just going to put it this way, that there is only one place in the world, maybe 2 places, where you can generate this kind of energy per particle. All right. The collision energy, so at the LHC, the Large Hadron Collider, Switzerland, that big 15-kilometer proton collider, all it does is collide two protons against each other as fast apart as possible. The average collision energy in the LHC is half a joule per collision. All right, so the only way that you in the world can generate a collision of this energy is at the LHC for one particle. All right, and it's about the energy of getting smacked in the head for baseball. Pitcher throws a baseball at your head. That generally has about a joule of energy. All right. Again, that's a lot of energy when you think about it. Imagine having a tiny little proton with not enough kinetic energy that it's equivalent to a baseball hitting you in the head. Right? It's a lot of energy. So therefore, it's a big frequency. I don't even know how to write this, right? This is, if we would write this in common units, this is 1.5 times 10 to the 11 terahertz, which is just a massive number, right? There's just nothing really terrestrial relevant at the scale. So this is why joules are not useful for us. Joules are just too big of an energy unit for microscopic values. Likewise, if we think about a frequency of 1 hertz, this is the energy over H, which means that the energy equivalent is 6.626 times 10 to the minus 34 joules per 1 hertz. Right? That's also an enormously small amount of energy. Right? So 1 joule is an enormously high frequency wave, or a 1 hertz wave. It's an enormously small amount of energy. All right, we'll just convert that to kilojoules per mole, because that's a number we're all more familiar with chemically. So I did it the wrong way. Right, this is 3.9. See that? Yeah, you can. 3.99 times 10 to the minus. There's 3 more units there. 10 to the minus 7 kilojoules per mole. Okay, so again, imperceptibly small amounts of energy. Remember, the typical bond strength for a carbon-carbon bond is about 400 kilojoules per mole. So this is why I tend to avoid using joules in this class, because they're just not useful units for us. They're either really massive or they're really, really small. We're talking about microscopic things, the amount of joules they contain is minuscule. If we talk about macroscopic objects and their frequency, they're ridiculously large. Okay. So what we want to do is just avoid joules and instead talk in a reciprocal unit that's more useful. And what we're going to find is that for low energy things, using hertz frequency as an analog for energy is very useful. All right, so we'll look at this hertz a little bit. So the frequency, light, right, a 1 hertz wave is H equivalent joules, H joules. Right? And it turns out that there are many very interesting things that go on in microwave radiation, in the hertz regions that we do in chemistry all the time. In NMR, the frequencies range from about 40, which is upstairs, to about 1100 times 10 to the 6 hertz, which is anywhere between 40 and 1100 megahertz. Or sometimes we call this, this will be 0.04 to 1.1 gigahertz. Okay, so these are the typical frequencies of the spacings and the energy levels of your spins, spin of the proton inside of your protons of your molecules, or for hydrogens, the hydrogen spins. Right, depending on the size of the magnet, those splittings, the energy levels you're looking have energy differences in the microwave, right? In the radios, we call it megahertz, gigahertz. Right. So NMR people use megahertz and gigahertz as their analog for energy all the time. Right? It's just the way we talk because right, their experiment in some sense is kind of on the order of a gigahertz, right? Their energy units are on the order of 1. Right? They're on the order of unity. And you'll see that that's kind of our trend here, is that we'll tend to choose units of energy that's when we talk about a certain problem that are small. They're on the order of 1 in those units. Right? And that just makes things easier, right? It's much easier for me to tell Charlie that my NMR is set up at 1.1 gigahertz instead of saying 1100 times 10 to the 6. Right? That's like 10, there's like 4 different ways that you could screw this up. Very few ways to screw this number up, right? Communication-wise, it's just much easier to work with these. And they tell you something meaningful about the experiment. You don't really get an appreciation for the difference between a 40 and 1100 megahertz instrument when you're looking between 40 and 1100 times 10 to the 6, right? If you put that 10 to the 6 into the constant, you really start to appreciate the differences. All right, there's a couple of really interesting kind of chemical type phenomenon in this region. One chemistry example. Is what's called the hydrogen recombination. Right? This is well known. We'll talk about this in a second. It has a famous wavelength of 21 centimeters, which is a frequency of, let me just double check. I think it's 1310, but let me just remind myself. Yeah, 1420. All right. And this is a very famous transition in hydrogen that's very, very bright and low energy. This is a transition. I'm not going to tell you, it's not really important what it corresponds to. We'll talk about it later, but this is a bright transition seen in emission in astronomical data. Right? We use this as a tracer for hydrogen. As a spectroscopic tracer or fingerprint for cold, neutral hydrogen. And I'll show you a really cool picture. I know it's on here somewhere. Yeah, let's see if I can get a nice thumb screen of this. All right, this is not the best picture in the world, but this is a picture of the Milky Way from the Earth, tuned at 21 centimeters. All right, so we're looking directly onto the plane of the Milky Way. And so this is the center of the galaxy right here. Right? And you can see along the plane, there's this really, really high density band of hydrogen here, right? This is where, in general, the highest density of stars are along the galactic plane right here. And there are these interesting regions on the edges, for instance, where there are these really, really bright clumps of very large dense hydrogen, which are generally considered to be very large star forming regions, a lot of young stars in these regions. And then there's a lot of bright hydrogen continuum around the center of the galaxy because there's a big black hole there in the middle, ultra supermassive black hole in the center of the Milky Way. And there's a lot of stars that orbit it, right? So you can map out the Milky Way and where where hydrogen is, right? How does the gas from stars flow in and out of the galaxy, right? And the idea is that these stars are the forgers of this hydrogen. You can see as the hydrogen kind of whisks away perpendicular to the plane, right? Like a wind. So there's always this constant wind of hydrogen blowing out of the galaxy. And you can use radio telescopes to look at this, and it comes from this frequency in particular, 21 centimeter. Right, you can actually take a satellite dish from DirecTV and point it at the sun, and if you get all the equipment right for it, you can actually do solar measurements of the 21 centimeter line just by using a DirecTV dish. It's very bright. All right, so that's frequency. We typically use it kind of in the microwave and the radio frequency region. So spectroscopists use frequency or energy in RF, radio frequency, and microwave applications. Right, for instance, the water in your hot pocket, right, resonates really effectively at 2.4 gigahertz in the microwave oven. That's why your microwave oven resonates at 2.4. Water is being absorbed within that region. Right, we always talk about that in gigahertz. Okay, so there's a reciprocal for frequency, which is wavelength, and that's also a useful unit to talk about energy, but with a caveat. Right, wavelength is an inverse unit for energy, right? Because since energy is equal to h nu, and nu, the frequency, is equal to the speed of light divided by the wavelength, right? Then energy in joules is equal to h times the speed of light divided by the wavelength. So it's an inverse unit. As wavelength goes up, energy goes down. Right, and the thing that I don't like about wavelengths is that when you calculate a difference of energy, this is a difference of inverse wavelengths. Right, and let's think, for instance, just kind of imagine this in your head. I won't do the math out. It's pretty easy to think about this. Imagine I change the wavelength by 1 nanometer. Right, so I go from 600 to 601 nanometers. All right, so my energy difference is 1 over 601 minus 1 over 600. Right, that's some number, right? But what about the energy difference between 300 and 301? Well, that's 1 over 301 minus 1 over 300. That's, again, the same displacement of wavelength, 1 nanometer. But 1 over 301 minus 1 over 300 is not the same number as 1 over 600 minus 1 over 601 or whatever. Right, so the ratio, fixed changes in wavelength do not correspond to fixed changes in energy, right, because of this inverse relationship. So wavelengths are a little problematic sometimes when you're doing energy calculations because of this. Just one problem, I'll just write here. Delta energy is dependent on the value of lambda. Delta lambda is 1 nanometer, and delta E is different if the initial wavelength is 300 nanometers or 600 nanometers. Okay, so it's nice, right? We can correlate directly to color, wavelength, and energy, right? We can say something about green photons and their energy, blue photons and their energy. That makes a lot of sense. But it's not very useful for doing energy calculations. It'll lead you in the, I mean, you can still do them, it's fine. It's just, it's not as easy as just subtracting two numbers in. All right, so where is this useful? Well, it's useful. Well, we use wavelengths kind of everywhere, but the place where we specifically use wavelengths a lot is in optical spectroscopy, right? The visible light. Wavelengths are commonly used in optical or visible spectroscopy. Oh, I just died, sorry. I got disconnected, everybody. Visible spectroscopy. All right, so let's just do a quick example, right? So a green laser pointer. So unfortunately, I didn't bring mine today. I would have otherwise. The wavelength of this is actually quite well known. It's 532 nanometers. Any normal green laser pointer you buy from Amazon is 532. It always is. It's the classic green laser pointer. How much energy is contained inside of this? Right, so let's calculate that, right? So energy is equal to H times C over lambda. So just roughly that's 6.626 times 10 to the minus 34 joule seconds times speed of light, which is 299,792,458 meters per second. And then our lambda, we have to do it in meters. So that's 5.32 times 10. Let's see, a nanometer is 10 to the 9. So this is 10 to the 11. 10 to the minus 11 meters. No, sorry. Wrong way. Minus 7. Sorry. 532 minus 7. Bless you. Half an angstrom, or half a micron. 10 minus 6. All right, well, let's just roughly calculate this. I'll work out the number, but this is minus 34 times 8. So that's 23. No, it's not. 25 plus 7. It's going to be around 10 to the minus 18, 10 to the minus 19 joules, give or take. Let's see how close I am. 6.6260 minus 34 times 299,792,458, 553,267. Yeah, I was right. Okay, so this is 3.73 times 10 to the minus 19 joules. Again, not a meaningful number, right? It's really hard to think what the hell is something that's minus 19 joules, right? But let's convert it to with Avogadro's number. Right, let's put it in moles and kilojoules. This is 225 kilojoules per mole. All right, now that we're at optical frequencies, optical wavelengths, joules are starting to come back into vogue again. Joules per mole, right? So optical frequencies, optical wavelengths, they tend to have, in some sense, per mole, chemical amounts of energy, right? This is about half the energy of the bond energy of like a CC bond, right? It's about 400 kilojoules. All right, there's a very good reason that when you have this wavelength, when you go to say, what would that half of this be? 260, 250, 240 nanometers. Anyone's done UV vis spectrophotometry on a solution, organic solution, you know that things tend to absorb very strongly around 230, 220, 200 nanometers. Right? At that point, we're starting to get around 500 kilojoules per mole of energy in our photons. And at that point, you're starting to get the chemical energy that's relevant to chemical bonds. And so that's why many organic molecules tend to absorb very, very strongly at just half this wavelength at 230, 250 because we're now finally getting at energies that are consistent with electronic excitations, chemical energy. Right. So as you'll see in right, this is almost enough energy to break some weak bonds. And you'll see this in rotation 3 in the lab. When you do the iodine lab, we're going to use optical spectroscopy. And when you sweep it around 500 nanometers, you'll see that the iodine molecule actually falls apart. Right? This is enough energy to break I2. So again, what we're finally seeing is that as we're starting to get towards optical frequencies, optical wavelengths, we're starting to return back to a region where we can start talking about thermal energy, kinetic energy, or kilojoules, a bit more mechanical. Okay, so but there's this whole kind of Goldilocks region we haven't talked about yet. We've talked about low frequency, or where we talk about things in hertz and frequency. Here we're looking at things in wavelength, which are high frequencies. Right, maybe we should quickly calculate what the frequency of 532 is. We'll come back to that in a second. But we need some unit that, in some sense, falls in between these two limits, right? We want something that scales with energy, right, like frequency does. Frequency and energy scale linearly. But we want it to not be a number that's just absolutely massive at intermediate energy scales, right? Frequency is, right, by the time frequency is relevant for chemistry, we're at millions of hertz. So, and here we're going to find that this is something like 10 to the 15, 10 to the 16 hertz. Right, so what about that region that's got like around 10 to the 10 hertz, 10 to the 9 hertz? Gigahertz, terahertz. And we have a better unit for that, right? So there's a unit that kind of falls right between wavelength and frequency, has best of both worlds. And it's called the wave number. That's not a real word. Both worlds. Now, if you've ever done infrared spectroscopy, you know what a wave number is, inverse centimeters. Right? So a wave number is defined, depends on who you ask, but usually it's a symbol, the little tilde on top of it. Sometimes it's also a frequency with a tilde on top of it. These are what are called wave numbers, and they're equal to 1 over the wavelength. Simple as that. They're inverse wavelengths. Okay, so the units of these are meters, inverse meters. Okay, and that's a really convenient unit to have because now it makes Planck's law E equals hc times the wave number. Right, we've multiplied everything out by c. That gives us an extra factor of 10 to the 9 for these small numbers. That really helps nicely. And we've returned back to something that is linear in energy. Right, delta E is hc delta omega wave number. Right, so we know 1. We move the energy by 1 joule. Doesn't matter what the wave number is. The wave number changes by the same amount. Right, so it's nice and linear. All right, by convenience or by convention, we use units of inverse centimeters. Okay, not inverse meters. Now that's kind of annoying because when we're doing calculations of H and C, they're in meters, right? But typically things are reported in wave numbers, which are inverse centimeters, and that's an experimental convenience, right? That's the experimentalist talking. If it were up to the theorists, we would never use wave numbers because they seem really stupid. We're literally introducing a complication into our units by having two numbers that are typically represented in meters and replacing our energy with something with wave C minus 1. You're just asking for someone to make a mistake. Right, but there's a reason why we choose centimeters because it's just in terms of where spectroscopy tends to operate, centimeters is the right choice. It's just spectroscopically very convenient. And the reason why is very convenient for spectroscopy. All right, and let's see why. Right, so if you have an omega of one inverse wave number, this means lambda, very easy to calculate, is 1 centimeter. Okay. And you can convert this quickly to frequency. It's not too hard. It's 29979.458 megahertz, which we often just round to, when we're lazy, to 30 gigahertz. All right, so a wave number, right, a unity wave number puts us kind of at the end of our hertz measurements, right? So we kind of don't go past a couple hundred gigahertz. At that point, we switch to wave numbers, right? A wave number is kind of, it starts at a point that's very useful for us, which is 30 gigahertz, right? It's kind of a really, really nice chunk of energy for microscopic chemistry, 30 gigahertz worth of energy, or one centimeter worth of wave. All right, so that's a super useful conversion. I do this conversion in my head all the time as a spectroscopist. This conversion is, and people wonder why I've memorized the speed of light exactly. It's actually because of this conversion. I've done it so many times, it's hard to not remember all these numbers. So it's really, really convenient unit to go from frequency, which is something you do in the lab with your light sources. And then when you're talking about chemistry, you want to use energy. Really, really easy conversion for us. All right, and then we could kind of look at where is this more typically used. Typically, if you're working in spectroscopy around one wave number, you still use gigahertz. So where wave numbers are typically used are in the hundreds or the thousands of wave numbers, right? When we're getting to slightly, they're large numbers, but not huge, not unwieldy. And so an example would be, right, the typical SP3 CH stretch frequency in the infrared is around the wave number, has a wave number of approximately 3,000 wave numbers. You probably remember that from organic chemistry. Right? Very easy for us to calculate all the properties, all the different energies for this. Right? So the wavelength is 1 over omega, which is 1 over 3,000 inverse centimeters. Which is 3.3. Why did it change my color? 3.3 times 10 to the minus 4 centimeters, which is 3.3 times 10 to the minus 6 meters, which is 3.3 microns. Okay, so this is another reason why we use inverse wave numbers, or we use wave numbers, is again, it puts us in a really nice place for infrared spectroscopy. These are kinds of, well, we haven't really talked about how infrared spectroscopy works, but infrared spectroscopy has some sort of length scale associated with the instrument, because there's a path length, there's these moving stages in the thing, it measures lengths of distances and paths, distances to calculate the spectrum. This is something called interferometry, which is about noticing how signals propagate through space depending on varying lengths of the path. And a wave number puts us in path length differences of about 1 centimeter, or when we're up at, chemically relevant energies, it puts us around a micron. And those are the kind of typical precisions we can have in an interferometric instrument like an FTIR. Right? There's always the resolution, if you will, and the energy, the frequencies that you can measure of an IR is a function of how finely you can move these two mirrors in measure, how finely you can move their and measure their motion. And so typically, up until very recently, typically the best we can do for precision on a motion of a physical object is about a micron. Right? So wave numbers are very large. Inverse centimeters are a very logical kind of scale for us to measure things that are differences in distances, because these are kind of the distances that we can reproduce easily with a mechanical system. All right, so that just comes from convention. It's purely convention. The people that started using wave numbers were experimentalists. It's not a number derived theory. It's a number derived from experiment. So the old infrared spectroscopists, people like Koblenz and Fraunhofer and a bunch of old farts that don't exist anymore. They're the guys who came up with this because it was just a convenient way to represent the data. So we use it a lot today. Wave numbers are also kind of nice because they kind of, again, they're Goldilocks number. They're kind of right in the middle of something really small and really big. So let me just give you a couple more conversions that are useful. And I use these all the time in physical chemistry because, again, often a paper will present some data in wave numbers, and I want to think about it in terms of chemical energy, kilojoules. Maybe I want to think about something in terms of temperature, Kelvin. There's lots of different kinds of ways I want to think about an energy. And wave numbers provide a really nice baseline for us to convert, kind of as a leap pad for all the other units. So let me get these units really quickly for you. So one wave number of energy is 11.96 joules per mole. Very convenient, right? It's just right in the middle. It's just about 1 joule per mole. Pretty typical number. This has an equivalent temperature of 1.44 Kelvin, right? Another interesting thing, right? If you increase your energy by 1 wave number, that's roughly equivalent to increasing the temperature of your system by 1 Kelvin. Very nice unit. And do I have any other ones that are useful? No, that's it. Those are probably the other two. Okay, so this is why you CM-1 wave numbers, we use them for everything. Because it's just a good unit. It puts us kind of in a relevant scale for thermal energy, relevant scale for mechanical or chemical energy, a relevant scale for length and frequency. Oh, let me do frequency. Oh, I already did frequency. 29979 458 megahertz. Right, so very useful unit. Right, really good to kind of remember the wave number. It comes up all the time in this class, and it comes up all the time professionally in chemistry as well. Really, really useful. Bless you. All right, I got one more for you, and then we'll probably stop for the day after that. All right. So what we've talked about, super low energy, chemically relevant energies, like optical into the chemical bond. Talked about the intermediate stage, which we use for wave numbers. What about the really high limit of energy? What if past optical? And when we start doing X-rays, ultraviolet, and we start blowing molecules and start ions, right? What kind of energy unit do we use? At that point, sometimes people still do use kilojoules per mole. Some people use wave numbers. I don't like either of them for this. Instead, we're going to appeal to a different unit that is rooted in some sense in the chemistry that's relevant at high energy. Right? We want to appeal to something that we can measure, that we typically measure in these high energy processes. And instead of appealing to light, we're going to appeal to the electron. This is called the electron volt. Right, the electron volt has a simple definition. The label we use for electron volt is lowercase e, uppercase v, EV. Definition of an EV is 1 EV It's the kinetic energy gained by an electron when accelerated from rest through a potential difference of 1 volt. Very simple experiment to do. Take 2 metal plates. One's positively charged, one's negatively charged. We'll ground positively charged plate. And we'll have a power supply feeding in energy at +1 volt difference. Right? That causes electrons to move from the anode to the cathode at 1 volt. And the energy of these electrons, is defined as 1 eV. Super easy experiment. Right. Electrons have a fixed charge. So every electron is equivalent, exactly the same, provides the same exact contribution of energy at the same voltage. So it's a really reproducible argument. Electrons are completely boring. They're all exactly the same. They all have exactly the same contribution. And so you can very easily measure them. And let's look at what 1 EV looks like compared to the other units. Wow, it's 96.48 kilojoules per mole. Again, chemistry, kind of chemical units here. Right? Once we get to 100 kilojoules per mole, start thinking bonds, right? Near bond strengths, ionization energies, things like that. This is 8,065.5 wave numbers. I'll give that to you in meters. I got my units from June. So that's right. So 6.5. Oh, times 1/1000. Sorry. So it's 123.9 nanometers wavelength. Okay. So 1 EV kind of puts you. Oh, I'm off by a factor of 10. Sorry, that's wrong. I knew that seemed really, really small. It's 1239. Sorry. 1239. Right, so it puts you 1 EV is actually, this is kind of right on the edge of red. Like you can't see 1239. Our cutoff is about 950. But so this is right at the edge of red in the infrared. This is what we would call the near infrared. So it's right outside the red. But it's right past the red limit of the thing, right? So 1 EV kind of is a mark for when optical starts. Most optical spectroscopy starts at about 1 EV. Beginning of optical. All right, and what are useful uses for this? Well, it's used, right? This is often used for ionization energies and other high energy processes. a great example, and this is one we're actually going to derive exactly in class when we get back. It's if you take hydrogen and break it apart, ionize it into a proton and an electron. This is the ionization energy of hydrogen. This energy is exactly 13.7 eV. This is kind of this is how we, in some sense, as we'll see, this is a number we can solve for exactly. We'll actually be able to calculate this number precisely. And it gives us a really, really good baseline to measure EVs, right? Anytime we put a hydrogen into a discharge and ionize it, we turn the voltage up. You put it in a tube, like a neon gas tube, in a gas tube with two electrodes at the end, right? You have a negative and a positive. You crank that power up, nothing happens, and then you turn the voltage to 13.7 volts, and then you get a discharge of blood. It flows at 13.7. So this is a really, really easy way to calibrate this energy very, very precisely. Right? You can use spectroscopy to do it very precisely. There's other ways that people calibrate this, the way you determine it, but it's a really simple way of doing it, right? To find out the voltage that causes hydrogen to start glowing. That's exactly 13.7 volts. It's often used as a mat. So people, we don't really use it in chemistry so much, but it's often used as an analog for mass, right? Because I remember what Einstein says, E equals mc squared. This means that the mass of an object is equal to its energy divided by c squared. So we often measure masses in units of EV over c squared. Right? This is how physicists talk about the masses of subatomic particles. They always report them in terms of these units, and electron volts versus c squared. Right? Because they're not actually measuring the mass, right? When they look at the Higgs boson, they look at the Higgs boson, they're not putting it on a scale, right? They're measuring the residual kinetic energy from some collision that generates it. And so they have some spectrum that at 125 EV, there's an absorption, there's some sort of excitation at the equivalent energy for the mass of the Higgs boson. So they have something that in X units, the spectrum looks like EV versus counts detection. And so they find this peak for the Higgs boson at 125. I'll write the number down in a second, but it's an EV. And that's equivalent to its mass because these particles are moving relativistically, moving near the speed of light. And so it's just as fine to report masses as energies. Right? So that's what they do for really big things. And so some examples. Masses. Let's do some things that you know first. So like the electron mass. So the mass of the electron is 0.511 mega electron volts per c squared. Right? The proton is much larger. It's about 1,000 times bigger. 938.3 mega electron volts per c squared. The neutron, of course, is actually very similar to the proton. I won't write it down. And then for fun, the Higgs boson, the last particle we've detected, this has a mass of 125 giga electron volts per c squared. So very, very big particle. Right? It's in some sense, what is that? 150 times, 130 times the size of the proton in terms of mass. Right? But again, remember that these are energies, right? Mass and energy are the same thing when you're moving near the speed of light. So even though you say, well, this is a really big particle, like why is this particle so massive, right? We think of it as an even more fundamental particle than a proton, right? And sometimes you have to dig down deeper and deeper to see the Higgs boson. But the point is that mass and energy are the same thing. So this only appears at very, very high energies. So particles that are generated at high energy excitations of particles at speed of light, near the speed of light, are corresponding to excitations of particles that have very large masses. So actually, in some sense, the stable particles are the small ones because they're low energy. And these big particles are very unstable because they're very high energy and therefore high mass. Okay. So that gives us 4 units of energy: wave numbers, frequency, wavelength, and electron. We'll use every single one of them in this class, right? Different contexts, right? We're talking about wave numbers and vibration. We're going to talk about angular momentum when we come back. That'll be a lot of hertz, a lot of megahertz, a lot of frequencies. And then we'll talk about hydrogen, the hydrogen atom. That will be all in EVs because we'll be talking about hydrogens and protons. That's an EV scale. And then we'll get to molecules where it might be more useful to go back to kilojoules. Right? Well, actually, molecules we kind of mix and match. So we'll use all the units. Just realize that they're all the same. They're just different conveniences, different contexts, different levels of convenience depending on what we're talking about. But these will be the units that we'll use going forward. Okay, I'm sorry for the dry lecture. I think it's important that we're all on the same page going forward because I know already that some of you are getting confused with all the soup of variables and numbers and things like that. So let's make sure that we're all on the same page. I'm done for today. We'll come back to harmonic oscillators next class. You guys have a lovely break.
Tomorrow, right?
You know what I mean? Yeah, I do. Send me your I'll get you guys. I haven't played all week today, so.
So
I'll get it. What level is you guys?
Finished.
Second run through? Good.
My roommates.
Yeah. So I'm gonna be out of town this weekend. I'll probably like add you guys on Tuesday.
But like, it made sense.
No,
But it's a little absurd.
Just send me your names, okay?
I was gonna say.
All right, cool. Break. Yeah, you too. You're not coming to Catan tonight? Oh, that's fine. Have a good one, Ian.
I'll be at Con.